In previous lecture, I derived first and second recurrence relation of Legendre's function. In today's lecture, I will derive remaining four recurrence relations of Legendre's function. As you can see on the top of this slide, first and second recurrence relations are written as equation number 7.16 and 7.20, which we already derived in previous lecture. Why these two are written on the top of this slide? Let us discuss. Before that, let me clear one more thing, that equation number 7.16 and 7.20 are the same which they were in previous lecture while deriving first and second recurrence relation. Actually, there is a basic difference between derivation of first and second recurrence relations and derivation of remaining third, fourth, fifth and sixth recurrence relation. These two derivations were quite independent in nature, quite original in nature, while when we derive third, fourth, fifth and sixth recurrence relation, we will utilize these two already derived recurrence relations. How? You can see, if we discuss derivation of recurrence relation third, from where we are starting? From recurrence formula 7.16. 7.16 means first recurrence relation. So let's begin this. Starting with that 7.16 or first recurrence relation, we are differentiating with respect to x. You can check it. Left hand side 2n plus 1 is constant. Then x invariant and differentiation of pn is pn dash. Then using product rule plus again that constant 2n plus 1. Pn invariant and differentiation of x is 1. In right hand side n plus 1 is constant and pn plus 1 is differentiated at pn plus 1 dash plus n constant pn minus 1 dash is differentiation of pn minus 1. Then what we are doing? We are eliminating x pn dash from two equations. Which two equations? One equation is that 7.21 which we just obtained. Another equation is 7.20, that is 7.20. Second recurrence relation. So you can check it. We are utilizing first and second recurrence relations at the time of deriving third recurrence relation heavily. And it will be the story throughout today's lecture. So here using 7.20, we know the value of x pn dash can be obtained and that can be substituted at that place in equation 7.21. By doing that, we obtain 2n plus 1, fine. Then in place of x pn dash, from there we have n pn plus pn minus 1 dash plus 2n plus 1 pn equals to n plus 1 into pn plus 1 dash plus remaining terms remains invariant. Then in next step, 2n plus 1, fine. What we are doing there? We are simplifying that step. And by simplifying that step is obtained. Next step is obtained. And continuously by simplifying, by taking commons for similar subscripts like pn plus 1 at one place, you can say pn minus 1 dash at two places. So by taking certain commons and etc. By simplifying continuously, we reach up to the required third recurrence relation, that is 2n plus 1 pn equals to pn plus 1 dash minus pn minus 1 dash, known as 7.22. Equation 7.22 means third recurrence relation. You have to keep that in mind. 7.22, say you can see it's coming in next derivation also. So you have to keep that in mind at least for this lecture, that 7.22 means third recurrence relation, 7.20 means second, 7.16 is first. These numbers are coming from previous lecture, and here in continuation of 7.20 we are having 2, 1 and 2, 2. So it's completion of derivation of third recurrence relation. Let's talk over fourth recurrence relation, which is, as you can see, simplest possible derivation. Why? Because what we are doing, we are subtracting 7.20, that is second recurrence relation, from 7.22, which is third recurrence relation. So it is nothing but subtracting second recurrence relation from third recurrence relation. Simply we are getting fourth recurrence relation. So it's a difference of two recurrence relations, nothing else. Before moving up to next slide and deriving remaining two recurrence relation, let us talk about one very important fact. Say if in examination you have to derive that third recurrence relation, which is based over first recurrence relation, that is equation 7.16. So what you have to do? You can utilize that directly. You should not derive that first recurrence relation. It is not required, at least if that problem comes in any kind of examination. You can utilize 7.16 means first recurrence relation. If you remember, you can utilize that directly. But that will not be the story if you have to derive fourth recurrence relation. You can't say that by just a simple subtraction the derivation is over. No. In that case, what you have to do? Say if it comes in examination, it is difference of two recurrence relations, 7.20 and 7.22. So you have to derive, dear students, you have to derive 7.20 independently, that is second recurrence relation, 7.22 independently, that is third recurrence relation, and then you have to take difference to produce or to derive fourth recurrence relation. Now we start derivation of remaining two recurrence relation, that is recurrence relation number 5 and recurrence relation number 6. First of all, while deriving recurrence relation number 5, from where we are starting? Recurrence formula 7.23. Do you remember? It is nothing but fourth recurrence relation. So we are utilizing the previous recurrence relations continuously, which we already derived. So by fourth recurrence relation, what we are doing there? We are just replacing n by n minus 1 in fourth recurrence relation. So we obtained one equation, is 7.24. And then we are multiplying equation 7.20. If you remember, second recurrence relation. 7.20 means second recurrence relation. We are multiplying it by x, and then we are subtracting that from equation 7.24, and by that difference we obtained 7.25 as fifth recurrence relation. Then sixth recurrence relations derivation is written there. We are starting from 7.16. As I already told, first and second recurrence relations are extremely important. We will utilize them continuously. As you can see, first recurrence relation 7.16 means first recurrence relation. And what we are doing there, we are writing first recurrence relation, and a tricky step is there. 2n plus 1 is broken in n plus 1. Then n plus 1 multiplied with xpn, and then plus n multiplied with xpn. And then we are mixing those two terms, n plus 1 xpn and n plus 1 pn plus 1 together, and then n xpn and n pn minus 1 are mixed in right hand side, and we obtain one equation. That is nothing but certain simplifications are done in first recurrence relation. We obtain equation 7.26, and then we are mixing two equations 7.25, that means fifth recurrence relation 7.25, and that just obtained equation 7.26. How we are mixing? Because you can see that n pn minus 1 minus xpn is very much there. So we are substituting value of that as 1 minus x square into pn dash, and we obtain 7.27, equation number 7.27 as sixth recurrence relation. So dear students, as you may have observed that derivations of third, fourth, fifth and sixth recurrence relations, especially for these four recurrence relations, nothing but what we did? We did clubbing different recurrence relation with different kinds of mathematical operations, which you have to practice for some time so that you can easily derive all 6 recurrence relation, as well as you have to memorize all these recurrence relation, because for deriving especially third, fourth, fifth and sixth, we utilize not only first and second recurrence relation, but also whenever required, third was utilized in fourth, maybe fifth was utilized in sixth, like that. Okay, so it was about deriving all recurrence relations for Legendre's function. In next lecture, we will be discussing practical problems based over recurrence relations or the previous derivation which we have already done.